In this video, we'll have an overview of web application security and discuss several common issues and techniques. There are three things when it comes to web security: authentication, authorization, and connection security. Authentication is a process of establishing the identity of a client. Typically, it involves asking the client for username and password. The server will check the username password, and if they match the ones on record, the server knows who the client is. Note that even though a client is authenticated, it doesn't mean the client can access everything. The server usually needs to do another check and see if the client has the privilege to access certain resources. This process is called authorization or access control. And because the client and the server communicate over the web, and the web is full of bad people, we must ensure that the connection is secure. So if someone is eavesdropping on the network, they won't get private information like your password or credit card number. Connection security is something outside the application, so we won't spend much time on this. Usually it's covered in a networking class or a security class. For us, just know that we need to use HTTPS to ensure connection security. To use HTTPS, you first need a so-called certificate. You can create one yourself called a self-signed certificate. Self-signed certificates are fine for development and for behind-the-scene usage, like for communication between two backend services. But browsers don't consider them valid certificates, so if you use them on a public server, you'll scare your customers away. These days, you can get free certificates from the organization Let's Encrypt, but you have to be the actual owner of a domain to get a certificate. For example, I won't be able to get a certificate for a Cal State LA server because I don't own the Cal State LA domain. Once you have a certificate, you can then configure HTTPS on your web server or on the embedded Kestrel server in an ASP.NET Core application. So now, assuming our connection is secure, what do we need to do in our applications? Well, security is really a very complex thing. Here we'll discuss a basic scenario and use it to discuss some fundamentals in web application security. Here in this scenario, we'll have an application that manages its own user credentials, for example, having a users table in a database. The authentication process will ask a client for username and password. Login here could be a login page in a web application or a login endpoint in a web API. After a client is authenticated, it may try to access protected resources, and the application needs to check whether the client is authorized to do so. This is a fairly simple setup, but there are a few important questions we have to answer. First is how to store passwords safely, and this applies to both web applications and web API. The next two questions are kind of related. What happens if authentication is successful, and how do we check subsequent requests? The answer to the first question is, instead of storing user passwords directly, we should run them through a cryptographic hash function and store the hashed password or password hash. For example, if the original password is ABCD, we would store something like this instead. This, of course, raises some questions of its own. The first is, why do we want to do this? Why not just store the original password? The obvious answer here is that we don't want anybody to see users' passwords, even the system administrators. But there's also a less obvious reason. Users tend to reuse their passwords on different websites and services. If an attacker breaks into one system and steals the user's password, they can try the same password on other systems. This is why we should only store password hash, so that even if our system is compromised, the attacker cannot get the user passwords to hack the user's other accounts. At this point, you may be wondering what's the difference between encryption and hashing, as they sound pretty similar. The short answer is encryption is reversible, meaning that you can take something, encrypt it, then later decrypt it to get the original. Hashing, on the other hand, is one way, meaning that in theory, you should never be able to get the original back. So then you may be asking, if I can never get the original password back, how can I check if a password is correct? Well, it's actually quite simple. You just need to run the password provided by the user through the same hash function, then check if the result matches the hash value stored in the database. Just hashing the password is not quite enough, as hashed passwords may still be revealed by attacks such as brute force attacks or dictionary attacks, or some combination of the two. Usually, an application should do more to make password hash safer, and that may include enforcing some password policy. For example, forcing users to use long passwords with special characters. It's also important to choose good password hashing algorithms. The current recommendations are Argon2, PBKDF2, Bcrypt, and Bcrypt. You should avoid using algorithms like MD5 or SHA, which have already been proven to be bad for password hashing purposes. One more important thing is to use sort. Sort is just a piece of random data generated for each user. Sort will be concatenated with the user's password to produce a hash. Having sort makes dictionary attack a lot harder. Without sort, you can pre-hash a bunch of common passwords and use it as a dictionary to go from hash back to password. But with sort, the dictionary has to be exponentially larger because one password now can have many different hashes when it's concatenated with different sorts. These days, I like to use Bcrypt for password hashing. This is what a Bcrypt hash of the string ABCD looks like. Note that this hash contains not just a hash value, but also some additional information, like the version of the Bcrypt algorithm used to create the hash, the so-called cost factor, which you can adjust to make the algorithm run faster or slower. Generally speaking, you don't want the algorithm to run too fast, because then it will be easier to crack passwords by brute force. But you also don't want it to run too slow, because then checking password would take too long. Right now, I think 10 to 12 is the recommended value for the cost factor. Note that sort is also included in the hash, which is nice because you don't have to use a separate column in your database table to store sort. For password hashing libraries, .NET Core has built-in support for the PBKDF2 algorithm. You can check out the documentation and see how to use it. For Bcrypt, the commonly used library is Bcrypt.net next. It's this one. The name is kind of a mouthful. It's because originally there's a Bcrypt.net project, which is a port of a Java Bcrypt implementation to .NET. So it's called Bcrypt.net. And later there's a fork of the Bcrypt.net to add more features and so on. Hence the name Bcrypt.net next. Anyway, let's do an example and see how it works. So this is the example we've been using for ASP.NET Core, and the first thing we want to do is to add the Bcrypt library. And we can see here that the package name is called bcrypt.net-next. So let's do the new get package thing. We'll search for bcrypt.net next. So yeah, it's this one. So let's grab that. Okay, so now we have added it to this project, and we won't be using this in a web application until next time. But for this video, we want to do a console application, just see how it works. So I'll add another project to this solution. And this one is going to be a console application, and I'll call it Bcrypt test and .NET 5, and let's create it. Note that this is a new project, and we added the Bcrypt package to the other project, the Web Application 1 project. So what we'll do here is we'll add a so-called project reference, and that makes the Bcrypt test project referencing the Web Application 1 project. What that means is that Bcrypt test will get all the dependencies of this project plus all the classes from this project. So this way we don't have to include Bcrypt package in this project. It's get from the reference project plus all the classes in the reference object. Anyway, here then we can say bcrypt net.bcrypt, and the method to hash a password is called hash password, and let's just hash the string abcd, and let's say we store this in a hash variable, and then let's print it out. So let's run this, change this to Bcrypt. Okay, so run this. And yes, so this is the output, and it's a Bcrypt hash of the original ABCD string. And to verify a password, let's say, for example, a user entered a password, and if we want to check if it matches the hash stored in the database, we can use another method called verify. So let's say a user enters a password. Let's say enter the password correctly, and then we'll write out bcrypt net verify. So verify takes two arguments. The first one is a text, and the second one is a hash. Okay, so first one is a password, the second one is a hash, and let's see. It prints out to true. So this verify method returns either a true or false. If the password matches a hash, it will return true, otherwise it will return false. So in other words, if we store the hash, a user enters a password, we just use this to check. And if the user enters the wrong password, for example, this verify would return a false. So then we know that the user didn't enter the right password. So all in all, pretty easy to use. You can check out the documentation for additional API, but the two most important ones are just hash password and then verify. Okay. So now we know how to store passwords and how to verify passwords. Let's talk about what happens next. If you remember, in CS3220, when we program web applications, we use session-based security, which works like this. If authentication is successful, the user's information is going to be stored in session. So it's going to be stored somewhere here. For example, it will have a session ID 123 and then some information about that particular user. And the session ID, in this case, for example, 123, is sent back to the client, usually in the form of a cookie. Then the session ID will be included in subsequent requests, and the server will use that session ID to look up the session data and see if it can find the user information for that session ID. Now, if the session ID doesn't exist, it means the user is not authenticated. Of course, then the user cannot do anything. If the session ID is found, then it will use the user information stored in the session to determine if this user can access the requested resource. There are some advantages to implement security this way. The most important one is efficiency. Because session data is kept in memory, when a request comes in, it's very efficient to check if the client is already authenticated and whether the client is allowed to access some resource. Another benefit is that it's easy to revoke access. We just need to remove the session data for a client from memory by doing a session invalidate, and this revokes the access for that client. But there are also some problems of using session. First, session data takes up server resources, and we'll have lots of users. That's already a big issue by itself. To make matters worse, because session data is kept in memory of the web server, it also makes it difficult to do the so-called horizontal scaling. When your application or web API is under heavy traffic and you want to increase its capacity, you can do two things. You can get a bigger server with more memory, faster hard drive, faster CPU, and so on, and that's called vertical scaling. The problem of vertical scaling is that you reach the limit of a single computer very quickly. Very soon you'll find out that there's no faster CPU you can buy or no more memory you can add to the same motherboard. On the other hand, you can try horizontal scaling, basically adding more servers. You can put a load balancer in front to distribute the traffic to different servers. There's almost no limit of how many servers you can add, so this is a much more effective way to scale. Except for one thing, if you use session data is kept in the memory of one server, so all subsequent requests from the same client will have to go to the same server, regardless of how many other servers you have available. Very soon you'll find that the load is no longer balanced. You'll have some servers that are very busy and some servers underutilized. ASP.NET Core implements security without session. Later, we'll use an ASP.NET Core authentication scheme called cookie authentication. The way it works is this. If authentication is successful, the user's information is encrypted and sent back to the client. It's encrypted so the client cannot tamper with the user information. And then the encrypted user information will be included in subsequent requests in a cookie. The server will look for this cookie to determine if the user is authenticated. If the cookie exists, it means the user is authenticated. Then the server will decrypt the user information in the cookie and use it to decide if the user can access a requested resource. There are two important characteristics about this scheme. First, the server does not keep session data in memory, so it takes less server resources, and that means it's good for horizontal scaling. Second, all the information needed for authorization can be kept in the encrypted user information. So we don't need to go back to the database and load the user information again to authorize a request. This is very good for performance as database access is much slower than decrypting some information in memory. Okay, so this is the end of this video. In the next video, we'll see how to actually program using ASP.NET Cookie authentication. Thanks and see you in the next video.